In evolutionary history, there occurred a time when animals started spending significant amount of time in upright position. This placed a number of demands of circulatory system. The venous system that returns blood from the lower extremities to the heart underwent changes. You will recall that veins are blood vessels through which blood returns to the heart. Humans and animals such as the giraffe have adapted the problem of moving blood upward against gravity. But animals such as snakes, rats, and rabbits will die if held upwards since the blood remains in the lower extremities and the venous system is unable to move it upwards the heart. Figure shows the average pressure observed in the arteries at various points in the human body. Since viscous effects are small, we can use Bernoulli's equation to understand these pressure values. The kinetic energy term half rho v square can be ignored since the velocity in the three arteries are small, approximately equal to 0.1 meter per second and almost constant. Hence, the gauge pressure at the brain Pb and the heart Ph and the foot Pf are related by this equation, where rho is the density of blood. Typical values of heights to the heart and the brain are 1.3 meters and 1.7 meters respectively. Taking blood density 1.06 into 10 raised to 3 kilogram per meter cube, we obtain that pressure at foot 26.8 kilopascals and pressure at brain 9.3 kilopascals. Given that pressure on heart is 13.3 kilopascal, which is measured by the sphygmomanometer. Thus, the pressure in the lower and upper parts of the body are so different when a person is standing, but are almost equal when he is lying down. As mentioned in the text, the units for pressure more commonly employed in the medicine and physiology are torr and millimeter of mercury, where 1 millimeter of mercury is equal to 1 torr and which is equal to 0.133 kilopascals. Thus, the average pressure at the heart is 13.3 kilopascal is equal to 100 millimeters of mercury. The human body is marvel of nature. The veins in the lower extremities are equipped with valves, which open when blood flows towards the heart and close if it tends to drain down. Also, blood is returned at least partially by the pumping action of associated with breathing and by flexing of the skeletal muscles during walking. This explains why a soldier who is required to stand at attention may faint because of insufficient return of blood to the heart. Once he is made to lie down, the pressure becomes equalized and he regains consciousness. An instrument called a sphygmomanometer usually measures the blood pressure of humans. It is a fast, painless, and non-invasive technique that gives the doctor a reliable idea about the patient's health. The measurement process is shown in the figure. There are two ideas why the upper arm is used. First, it is at the same level as the heart and measurements. Here give values close to that at the heart. Secondly, the upper arm contains a single bone that makes artery there, called the brachial artery, easy to compress. We have all measured pulse rates by placing our fingers over the wrist. Each pulse takes a little less than a second. During each pulse, the pressure in the heart and the circulatory system goes through a maximum as the blood is pumped by the heart, systolic pressure, and minimum as the heart relaxes, diastolic pressure. The sphygmomanometer is a device which measures these extreme pressures. It works on the principle that blood flow in the brachial upper arm artery and made to go from laminar to turbulent by suitable compression. Turbulent flow is dissipative and its sound can be picked up on the stethoscope. The gauge pressure in the sac wrapped around the upper arm is measured using a manometer or a dial pressure gauge. The pressure in the sac is first increased till the brachial artery is closed. The pressure in the sac is then slowly reduced while the stethoscope placed just below the sac is used to listen the noise arising in the brachial artery. When the pressure is just below the systolic peak pressure, the artery opens briefly. During this brief period, the blood velocity in the highly constricted artery is high and turbulent and hence noisy. The resulting noise is heard as a tapping sound on the stethoscope. When the pressure in the sac is lowered further, the artery remains open for a longer portion of the heartbeat cycle. Nevertheless, It remains closed during the diastolic minimum pressure phase of the heartbeat. Thus, the duration of the tapping sound is longer. When the pressure in the sac reaches the diastolic pressure, the artery is open during the entire heart cycle. The flow is, however, still turbulent and noisy, but instead of a tapping sound, we hear a steady, continuous roar on the stethoscope. The blood pressure of a patient is presented as the ratio of systolic diastolic pressure. For a resting healthy adult, it is typically 120 to 80 millimeter of mercury or 120 to 80 torr. Pressure above 140 to 90 require a medical attention and advice. High blood pressure may seriously damage the heart, kidney and other organs and must be controlled.